Today we're covering note 2.3, which is solving graphing absolute value inequalities. So similar to what we did in 2.2 with the equations. So when an inequality contains an absolute value expression, it can be written as what we call a compound inequality. So the absolute value of x is less than 5. Well, that's all the real numbers whose distance from 0 is less than 5 units. So that's all the numbers between 5 and negative 5. 0, 1, 2, negative 1, negative 1.5, negative 2.5. So that can be written as x is less than 5 and greater than negative 5, or what we call a compound inequality. X is less than 5 and x is greater than negative 5. Or as an interval, that would be from negative 5 to 5. That would be an interval notation. So we're going to solve it very similar to like we did equations. We're going to almost always have those two cases, positive case and a negative case. So we're going to add 3 to both sides. Oops, this is an x. So absolute value of x is less than 2. So what are the numbers that have an absolute value less than 2? Those are all the numbers that are less than 2. But it's also all the numbers that are greater than negative 2. So 1, 0, negative 1, negative 1.5, negative 1.75, and so forth. So x is less than 2 and greater than negative 2. Or it's negative 2 to 2 as an interval. On a number line, right, same idea, 3 numbers, 0, 2, negative 2. So it can equal 2, and where are the numbers less than 2? They're to the left. Where are the numbers greater than negative 2? They're to the right. So these arrows are going to end up touching. Now the reason I draw it off the number line, because I think visually this is easier to see. If you look at books or maybe on online, you might see the arrow on the number line. To me, that's just a little harder to read. Why is it an open dot? Because they're less than symbols. There's no equal to underneath. All right, next example. Absolute value of x minus 1 is less than or equal to 2. So the solution would be all the numbers less than or equal to, and all the numbers that are greater than or equal to negative 2. All right, again, this is an and. So again, just like we did the equation, positive case, negative case. So to add 1 to both sides. Okay, so x is less than or equal to 3 and greater than or equal to negative 1. Again, as you read this compound inequality, you start inside. So x is less than or equal to 3, x is greater than or equal to negative 1. As an interval, that would be negative 1 to 3. And again, there's square brackets this time because it's less than or equal to. And then on a number line, same idea, just need the 3 numbers. So negative 1, 3, 0. This time they're going to be solid dots. Where are the numbers less than or equal to 3? They're to the left. Where the number is greater than or equal to negative 1? They're to the right. So those arrows are going to end up touching. Kind of forms like a little rectangle. And again, notice you get the same diagram. And every time it's a less than symbol, these are going to be the same. The only thing that's going to be different are the numbers and whether they're open or closed dots. Otherwise, they're still going to always go towards each other. So now, last one here is a little more complicated. So I'm going to add 6 to both sides. Then I'm going to divide by 3. Now, just a reminder, because it's going to come up later, remember when you multiply or divide by negative, you have to flip the inequality. I divided by a positive 3, so I don't have to do anything with it. So now I ask myself, can you have an absolute value less than or equal to 10? Yeah. 9, 8, 7, but also negative 4, negative 5, negative 6. So these are all the numbers that are less than or equal to 10, and all the numbers that are greater than or equal to negative 10. So that would be negative 9, negative 8, negative 7. And so, right, add 5. divide, divide. Right? So x is less than or equal to 2, but greater than or equal to negative 1, or negative 1 to 2. And on a number line, again, 3 numbers. We have 2, negative 1. Pick a number in the middle. There's solid dots because it's less than or equal to. All the numbers less than 2 are to the left. All the numbers greater than negative 1 are to the right. And you get the same diagram that we got on the last two. So again, right, you have those two cases. All the numbers less than less than 10 and greater than negative 10. Very similar to the equation, positive and negative. So we did equal in 2.2. Now 2.3 we did less than. What about the numbers greater than? Okay, so same idea, right? The absolute value of x is greater than 5, so that's all the numbers that are less than negative 5 or greater than positive 5. So as an interval, that would be negative infinity to negative 5, union 5 to infinity. I need the union because I'm skipping all the numbers in between negative 5 and 5. They're parentheses because we're not including negative 5 and 5. So same idea. We're going to solve it just like we did the last three. What numbers have an absolute value greater than or equal to 3? So that would be numbers like 4, 5, 6, 7. But it would also be numbers that are less than negative 3, like negative 4, negative 5. Now, is this an and or an or? Well, this is going to be an or. Why is it an or? Well, think of a number that is greater than 3 and less than negative 3. There isn't one. You're either greater than 3 or you're less than negative 3. So this is why that's an or. Same way, though, I'm going to solve it like the last three. Right? We're going to subtract. So we get negative 5. Subtract. So negative 11. So as an interval, that would be negative infinity to negative 11. Oops. Negative 5 to positive infinity. And then on a number line, sketch it the same idea. 3 numbers. Negative 5, negative 11, I don't know, negative 8. Greater than negative 5, go to the right. Less than negative 11 to the left. So this time the arrows go away from each other. And as you do this, either your arrows are going to go towards each other or away from each other. Those are the only two cases. Okay, next one. Absolute value of 5m minus 9 is greater than 24. So that's all the numbers that are greater than 24. 25, 26. Or it's all the numbers that are less than or equal to negative 24. Negative 25, negative 26, and so forth. Same idea, right? Solve. Right, add 9 to both sides. So 33, negative 15, divide. So 33 over 5, negative 3. So it's one or the other. Right, put this on a number line. Again, 0, 33 over 5, negative 3. Solid dots because it's less than or equal to. Right, numbers less than negative 3 are to the left of it. Numbers greater than 33 over 5 are to the right. So you get the same diagram. Again, these two are the same because it's an or. So the arrows go away from each other. If it was an and, like the first three we did, they're going to go towards each other. Solid dot because they have the equal bar underneath. Wait, these last two here are special cases. So absolute value of x plus 1 is greater than negative 5. So is there a number that has an absolute value greater than negative 5? Yeah, 0, 1, 2, 5, 10, 20, negative 5 is 5. So actually all numbers. So every single number you plug in here for x is going to be greater than negative 5 because the smallest absolute value can equal is 0. Well, 0 is greater than every negative number. So this is actually all real numbers. Any number you plug in will give you a value that is greater than negative 5 when you take the absolute value of it. Now if you go to the next one, notice the only difference between the two problems is now it's less than or equal to. So you need a number that has an absolute value less than negative 5. Well, 0 is the smallest. Well, 0 is greater than every negative number. So this one has no real solution. So two very similar problems. So when you go through and do this, and you get the absolute value isolated, and you get a negative, you have to understand, well, okay, it's going to be real solutions or no solution, depending on the sign. Right? We had the same thing with the equal sign. Right? When it equal to a negative number. That wasn't possible. That was no solution. Right, go ahead and flip your notes over. Now, when you get here to example 3, be careful. Yeah, I get that to negative 10, but don't just say, oh, the answer is no solution. No, I didn't say that. I said when the absolute value is isolated. It's not isolated. Multiply by negative 2 over 1. Now it's going to be isolated. Now, whatever happens on the other side, now I can make a claim. Well, this is 20, but now remember we have to flip the inequality because we multiplied by a negative. Anytime you multiply or divide by a negative, the inequality is going to flip. So can you have an absolute value greater than 20? Yeah, 21, 22, negative 21, negative 25, negative 26. So all the numbers that are greater than or equal to 20 or that are less than or equal to negative 20 are going to be solutions. So subtract 2, subtract 2. So as an interval, that would be negative infinity to negative 22, union 18 to infinity. On a number line, again, I just need the three numbers, negative 22, 18, pick a number towards the middle, so I'm going to pick 0, solid dot for both of them. Where the number is greater than 18, they're to the right. The numbers less than negative 22 are to the left. And again, because it's an or, the arrows are going to go away from each other. Again, why is it an or and not an and? Because there's no number that is greater than 18 and less than negative 22. It's either one or the other. Okay. Divide by negative 2 means we have to flip the inequality. Now, is there an absolute value that's less than negative 5? No, there is not. So this is no solution. Again, 0 is the smallest one you can get, smallest value. Right? 0 is 0 units from 0. There's nothing smaller than literally being on top of 0. Okay. So last two here, 4 and 5, or actually just 4, but there's two examples. We're going to do just like we did with 2.2. Now we're going to solve it graphically and algebraically. So graphically, we're going to graph the two functions. So f of x equals absolute value of x, right? Vertex hasn't shifted, 0, 0. It's V-shaped. It's going to open up. The slope is 1, so up 1 over 1. Right? Use the symmetry. So there's my function. So that's f of x. Okay, now g of x is a horizontal line. Slope is 0. So go up to 4. 1, 2, 3, 4. And there's my slope. Okay. So that's g of x. So highlight the portion All right, so highlight from where of g of x that satisfies that inequality. So where is g of x, right? So the green line, I'm highlighting only the green line, such that the part of the line is above the blue part. Well, okay, that might be a little confusing right now, so we'll come back to that. Let's solve it algebraically. So solving algebraically, absolute value of x is less than 4. So that would be all the numbers that are less than 4, all the numbers that are greater than negative 4. So this would be and, right? X is less than 4 and greater than negative 4. Right? So it's from negative 4 to 4. So when it asks me to highlight, right, the part of the line, so for me the green line, where the line is greater than the blue graph, that's this part right here. And if you look closely, that's from 4 to negative 4. That's the part we highlighted. So from negative 4 to 4. So there we go. Okay, example 4, second one here. So g of x, you do that one first. It's a negative absolute value. So the vertex is still 0, 0, but it opens down now. All right, slope is still 1. Okay, so this is g of x. And then we're going to do f of x is a horizontal line, right? Slope is 0 and negative 1. So that's f of x. So we're going to highlight, we'll come back to that. Just solve it algebraically. So g of x, negative absolute value of x, is greater than or equal to negative 1. Divide, you got to flip the inequality. So the numbers are going to be less than or equal to 1 and greater than or equal to negative 1. So x is less than or equal to 1, greater than or equal to negative 1. So if I was to highlight, that's this part right here. So this would be negative 1 to 1. So again, as you're going through and doing this, as you're solving, understand, right? It's going to be an and or an or. It doesn't really matter if you know that too much. As you go through and solve it, it'll become clear. But understand, when you're solving, you're usually going to have two cases, right? Notice, again, as we did this, one case, two case. One case, two case, right? One case, two cases. One case, two case. So understand that you're going to get two cases. That's usually the biggest problem students make, is they solve the first one perfectly, but they forget that there's actually other numbers, and it's usually the negative numbers they forget, because you're taking absolute value. It's that distance from 0. So when you're done with these notes, please make sure you write your summary.